In this calculus video, we're going to look at ways in which we can find the derivative of functions that have the natural log in them. But before we do that, what if we look at some quick examples of logs and review how they work? Remember that logs are exponents. So when we see a problem like log of 10, or natural log of 1, or natural log of e, all that means is we're looking for the exponent that will turn that base into the given argument. So, for example, log of 1. Well, what exponent will turn that base 10 into a 1? The exponent has to be 0. So the log of 1, we should always remember to be equal to 0. Natural log of 1 is also 0. Log base 19 of 1 is also 0. So remember, the log of 1 is going to be 0. How about log base 10 of 10? Or log base 42 of 42? When the base and the argument are the same, again, what exponent will turn the 42 into a 42? Or what exponent will turn the 10 into a 10? That's going to be 1. Likewise, the natural log of e. Well, the base there is e. And what exponent will turn e into itself? Again, that'll be the exponent of 1. So here are just 6 quick examples to remind you about how logs work. So again, it was 0, 0, and 0, and then 1, 1, and 1. Now in this activity, I have a list of log properties that can be practiced here by matching. So we want to make sure that we know our log properties and that we can use them. So here are 9 statements and then the matching solutions across right there. At the end of this video, I'll share with you the solutions to all of those, but this would be a great time to maybe pause this video and try those on your own to see if you remember how the log properties work from Algebra 2 and pre-calculus. At this point, I'm going to move ahead and talk about how to find the derivative of the function f of x equals the natural log of x. So let's take a look here at what that looks like. I graph here just a rough sketch of y equals ln of x. It starts kind of hugging the x-axis down low, increases, passes through the point 1, 0, and then it levels off a little bit, but it's always increasing. And because f is always increasing, what does that tell you about the derivative? If I analyze the little tiny slopes, or the tangent slopes of this function curve from its left domain all the way to the right domain, I see very, very steep, very high, very strong positive tangent slopes. But then as we travel closer to the x-axis, the slopes become a little bit less positive, and then a little bit less positive, and even less positive as we move across to the right. So I would maybe say that because f is always increasing, I would expect that the derivative here, f prime of x, would always be positive, since the slopes are always positive and since f is always increasing. Notice also the domain. The domain of this function only exists for values between 0 and infinity. So I actually graphed this also on Desmos. Here's the picture of the natural log of x in red. But here I also have the derivative of whatever is graphed over there for f of x. So I turned on the derivative function here in blue, and we kind of see this relationship existing between the natural log of x and its derivative. So sure enough, the derivative is positive throughout its domain. The domain matches the domain of the natural log from 0 to infinity. And it's always up there in quadrant 1. And so my question for you is, where have you seen that function before? And maybe we haven't seen that function by itself before because we might be more familiar with what it looks like across its entire domain, and that is the reciprocal function. What we're looking at on Desmos and what we're sort of exploring is that this sort of first quadrant graph of slopes is the reciprocal function, but it's only defined on the same domain of the original natural log function from 0 to infinity. The reciprocal function has on its domain negative infinity to positive infinity with the exception of 0, where we have a vertical asymptote. But we want these domains to match. And so for this derivative, we're only looking at this sort of upper right first quadrant section of the 1 over x reciprocal function. But that is, in fact, the derivative of the natural log function. Now, what are we going to do with that in calculus when we're asked to find a couple derivatives using the natural log? Well, here are the three steps. We can say right here that f prime of x is going to be 1 over x on the domain x is greater than 0, which is called the reciprocal function. And then I have this little mark here. Don't forget the chain rule. So just like we had 3 rules for exponential derivatives, and here they are, recopy, and then multiply by the natural log of the base, and then we multiply by the derivative of the exponent. So those are the 3 steps for exponential derivatives. For the log function, the natural log function, here's what we do. Start by using log properties to see if you can simplify the function somewhat. Can you manipulate the function to make our calculus easier? Use algebra, use algebra 2, use pre-calculus laws and properties, mathematical laws and properties that will help us simplify the function before we dive into the calculus. And we may not be able to, but if you can, go ahead and try that. Step 2, write the reciprocal of the argument. And step 3 is the chain rule step. Multiply by the derivative of that argument. So let's kind of see how these steps might be put into action. I just made up an example for you here. F of x equals the natural log of 3x minus 4 quantity squared. Find f prime of x. So what I would maybe want to do first here is utilize a log property. And if I have the log of a power, then I can actually swing this exponent out in front of the log, making it a multiplier on the expression. So this is really equal to 2 times the natural log of 3x minus 4. And that first step, if I catch that log property, really helps make the calculus that much simpler. So there's my algebraic massaging of that function. Let's now dive into f prime. The rule says, oh, by the way, that 2 is a multiplier. I'm just going to carry it over and not do anything with it. So 2 times the derivative of natural log. So take the reciprocal of the argument, 1 over 3x minus 4. But don't stop there, because the chain rule says we want to multiply by the derivative of that argument, and the derivative of 3x minus 4 is 3. I'm going to mark that and just put this little note right here that that little 3 comes from the application of the chain rule in this logarithmic differentiation problem. So there are the 3 steps. Step 1, use log properties. That was this step up here. There's 1. Step 2, write the reciprocal of the log argument. And that's this middle step right here. And then step 3 was to utilize the chain rule, which is that constant of 3 on the outside. Final answer, f prime of x is equal to 2 times 3 in the numerator, so 6 over 3x minus 4. And there's my derivative. Let's practice. Look at the hint. Log properties first. Make your calculus as easy as possible by using laws and properties and mathematical rules of algebra before you dive into rules of derivatives, which can be more complicated. So looking ahead here at letter A, got a series of examples that we'll work out together. At this point, again, a great moment to pause the video and try them on your own, or watch one example and then pause the video and move forward and see if you can figure these out by yourself. Function is natural log of x cubed. I'm going to use a log property here and call that 3 times the natural log of x, just like that. dy dx will be 3 times the derivative of ln x is 1 over x, the reciprocal. And then if I go times 1, which is the derivative of my argument, doesn't really matter. I'm going to end up with a 3 over x in the end. So derivative is 3 over x. That's my answer column over there. How about the natural log of cosine? The natural log of cosine. So the rules for logarithmic differentiation here with natural log. No properties to use here, so I'm going to skip that first step. How about we write the reciprocal of the argument? So 1 over cosine. 1 over cosine, times, here's the chain rule, times the derivative of the argument. The derivative of cosine is negative sine. So there's the reciprocal, and then the chain rule application. The derivative of this function is actually negative tangent. Negative tangent. Negative sine over cosine. There's dy dx. What about if the argument is a polynomial? So next one down here, y prime, a negative 400 is my multiplier. So I'll move that off to the side. Here comes the natural log piece. So 1 over x to the 8th minus x plus 1, and then multiply that by the derivative of the argument. So kind of a big 8x to the 7th minus 1. The derivative of the plus 1 goes to 0. So there it is. I'll put the negative 400 up in the numerator. I'll put my binomial also in the numerator, all divided by the power of 8, degree 8 trinomial. So there's the derivative. And then 2 more to go here. We have the natural log of 5 to the x. What if I use a log property? Swing that exponent out in front, make it a multiplier. So I have x times the natural log of 5. And here, be careful, because the natural log of 5 is a number. It's a constant. It's a value. I mean, think of how you would write the derivative of 3x. If my function was 3x, the derivative would just be the constant of 3. This problem is no different. Natural log of 5 is my constant. It's natural log of 5 times x. So the derivative, y prime, dy dx, would be just ln of 5. And then finally, in closing, we'll do letter E. So another exponent swing. I can call that x times natural log of E. Natural log of E is going to equal 1. So I'll cross that out and just think of it as 1. X times 1 is x. This is x times 1. And if my function can be simplified down to x, then its derivative will be simply 1. So there are some examples on how to find the derivatives of natural log functions. Don't forget the rules again. Use those log properties to simplify first, and then its reciprocal, and then its chain rule. Now, I promised you some solutions to the log matching activity at the front, so let me go there next. Here they are. Go ahead and grade your own, maybe pause the video and check your work and see if you were able to find the correct property solutions to all these logarithms. Logs and exponents are inverse functions of one another, so they kind of go hand in hand. Also, in calculus, when we talk about derivatives of exponentials, the derivatives of logs follow suit right afterwards. So I hope this video was helpful to you. So good luck as you practice writing derivatives of exponential functions and now logarithmic functions.